So the title of the talk that I gave is Earth, Moon, Mars. And Earth, Moon, Mars is a program we started like 15 years ago. We started with some activities on data and science, analyzing data from previous space missions that included the mission to the moon or Mars Express, also some astronomical observatory, or even experiment on the International Space Station. The second pillar is the development of technology, in particular in the area of instruments, payload, and also some cooperative robotics. I'll describe some of this project. And then at some participation to some space mission in some area of technology, but also of science, mission like mission to the moon, Mars, but also I was part of a mission on solar heliospheric observatory, on coral, also on some various astronomical telescopes. So we have also developed some laboratory and field activities to analyze materials, to analyze samples in particular. And this goes also into resources that we could exploit in the future. Resources, there are some material ones, but the most important one are the human resources. So the young professionals that we have to train and integrate in some of the teams of research, teams of projects. And in this, we have created an academy, so EarthMoonMars Astronautics Training Academy, where we describe, we do space science, space technology, but also we do humanities, social science. We train some astronauts, and also we have developed business innovation training. So that's a new aspect that we incorporated 4 years ago, innovation, business, entrepreneurship. I have been a long collaborator of the Space Business Innovation Center that we have here at ESTEC in the Netherlands already 15 years ago. But more recently, we had a platform, Eurospace Hub, with 6 universities and some NGOs funded by the European Union, developing some formation for young professionals into business and entrepreneurship. But in fact, we train them together with space researchers or also astronauts and candidates. Another important dimension, more and more critical, is space for peace. So we use our international cooperation to develop a peace further. I hope we can advocate that. So I have also some collaborators and students, in particular with the Space Renaissance International, the foundation that is promoting space for all. We have developed some action. And also we try to involve a large part of the society, so not only the scientists, engineers, and the agencies, but also the society at large, the cultural world, the art. And so we have developed some program with humanities, art in space. So I will share also some news from recent events, from international events that we had last year, organized by the IF, International Astrophysical Federation, where I was chairing a committee, but also organizing session every year at the International Astrophysical Congress, but also at COSPA, that is organizing every 2 years a large assembly. So last year was in Busan in Korea. Next year, that will be in Italy, in Florence. And we have also some activities with the Space Renaissance Center. Here, as a visualization, are things that illustrate some of the activities we do, analyzing data, contributing to mission, developing a system like a lander and testing it in the field. And we have also built a base, a Moon Mars base in Hawaii, but we have also access to other bases in Poland and also here in the Netherlands. And we develop also some instruments that could be used in some of these Moon Mars analog laboratories. So let's go back to the first theme, is the science of analyzing data from space missions. I have been co-investigator of the Mars Express mission, in particular of the high resolution stereo camera, HRSC, and this mission launched in 2003 has delivered a large number of science discoveries, even though it was quite a medium cost mission, total cost of 300 million euro, but very well done, and using also state-of-the-art instruments which were developed before we even we proposed the mission. So we have delivered some beautiful imagery in 3D of the surface of the moon. We have this way we have also been able to monitor the signature of events in the history of Mars. We have also had some instruments studying the atmosphere, the meteorology and climate of Mars, and even studying the aeronomy, the escape, and the interaction with the solar wind. And from time to time, we were getting close to the Phobos, and then we analyzed the Phobos moon of Mars. Here are some views of some studies that we have performed on the geology and also on the past history of Mars, where we found that there were some episodes of early wet Mars. We found also some remnant of mega floods, some episodes very catastrophic that took place on the surface of Mars. We found also some evidence of buried ice in even at tropical latitude. And we can also use this imaging to study the entire evolution, the tectonic signature of the entire evolution of Mars. One instrument that was very rich in scientific discoveries was the infrared imaging spectrometer, Omega, that had the ability to measure the mineral composition, observing in the infrared spectrum, so until 3.5 microns. This allows to measure minerals on the surface of Mars. Often they are covered with dust, but there are some areas, some outcrops that are really linked to the bedrock. And so Omega could analyze some of these exposures, in particular, could find some minerals like phyllosilicate or clays that trace back to the time where there was possibly some wet condition on the surface of Mars. And of course, Omega is measuring also the signature of some volcanic rocks, which were then also at question, altered by water. So putting the imaging at high resolution together with some of the imaging spectrometer, we have also some idea of the strata of the different minerals and how they were placed in different regions. Mars Express also had on board a very interesting instrument, a radar, long wavelength radar that had that was deployed, and so sent radar signal, got the echo, and was able to map not only the surface but also the subsurface. And in particular, it was able to measure the echo from the polar caps on Mars, measuring the depth, the thickness of 3 kilometers from its polar caps. And but also by some successive track over the southern polar layer deposit, it was able to find some signature of possibly some liquid water, or possibly brine under the glacier. And also radar, this one at long wavelengths, and also other radar that were flown later with Mars Reconnaissance Orbiter, have found the signature of water ice deposit even in tropical latitude. Actually, that's something that we also found on this Mars Express analyzing imaging data. Also with Mars Express, Martian year after Martian year, you can see the evolution of some of the important atmospheric quantities, the temperature, of course, but also on the top, the water vapor. So you see seasonal variation for that. Even the ozone, which is actually anti-correlated with the amount of water. We monitor also the oxygen and the dust. So there is some season where you can have some dust storm. It's not completely repeated Martian year after Martian year, like for instance, on this Martian year 28, you see a really gigantic, catastrophic dust storm that took place. In general, we try to avoid to have a mission operating during the dust storm season. So for the future, we try to go beyond. So we have looked at the history of Mars, its internal evolution, its the history of water, but now we try to look at the history of carbon and of possibly some chemical compound that could be prebiotic. And so we are targeting the very ancient terrain, so in the Noachian, so around 4 billion years ago, where we found some clays which were formed by this presence of water, but also that were able to trap some of the possible organics that were present there. And so we have selected some for some goals. And as you know, as a function of time from the formation of Mars 4.5 billion years ago, when there was an episode where there was possibly some surface liquid water, then with time, the water table has retreated under the surface. And so the surface of Mars is mostly dry and cold. And so we are searching for life at this period of the Martian history, where there could be sediment which were deposited. And we look also at places where there could be hydrothermal processes that are favorable for life. And but we want also to access sites where this signature have been preserved, and in particular preserved against radiation that is in fact sterilizing the top 2 meters of the surface of Mars. So we found some prime target, also taking into account landing ellipse technical constraint for safety. And we have defined a mission, ExoMars. This mission was proposed about 20 years ago, but it took time really to build it on. It was after the success of Mars Express, but the failure of one small lander that we had on board Mars Express, which was a bigger 2-lander. So we had also a priority to build a mission to search for life on Mars. And we called it ExoMars rover. And this mission initially was in collaboration with the United States, but the United States abandoned ESA. And then we have to find another partner for this mission. And we worked for 15 years with Roscosmos to build it. But unfortunately, in 2022, we were ready to, the rover was built, we were ready to launch. Everything was working very well, but because of the conflict in Ukraine, ESA stopped all collaboration with Russia. And then we had to find another partner. And so the mission was postponed from 2022 to 2028. And we do it in collaboration with the US, but we will have to build our own lander, and we have a descent system where we collaborate, and we have the rover that is built. So the rover has a suite of very sophisticated instrument to navigate. There is a camera, also panoramic camera. I'm co-investigator of this camera, but there are also spectrometers and a radar. And as well, there is a drill that will go down to 2-meter depth and will extract some samples and will analyze their composition, also organic, and with a suite of very sensitive instruments. So that's about Europe to Mars. In the meantime, our Chinese friends landed on Mars with the Tianwen mission and the Zhurong rover, and also with a suite of instruments, very interesting, ground-penetrating radar, and they could detect subsurface layers. They had a magnetic field detector, they had a meteor instrument, they could measure also some surface compound, and a multispectral camera, and they had, of course, on the rover navigation camera. Another rover, so a suite of rovers, we had launched the same year as Mars Express in 2003. We had the Mars Exploration rovers, Spirit and Opportunity, and then we had the Curiosity rover, and then now the Perseverance rover with also a suite of very sophisticated instruments. There was also on the Perseverance drone vehicle that did more than 60 traverses. And now we are making use of this for four goals: the geological study of rocks and the landscape, study the history; astrobiology, looking at whether the place was suitable for life and if there are some signs of ancient life. But also, curiosity is Perseverance is caching some samples, collecting samples that could be brought back to Earth by a Mars sample return mission. And its objective is to prepare for humans to go to Mars. We should be careful because, of course, we have to wait to be sure if there is no life on Mars before we send our own life there. And there on the Perseverance, we have a set of instruments, a mast camera, a pan camera, an environment analyzer. There is also in situ resource utilization experiment, MOXIE. We have also an instrument in X-ray that can measure the composition of rocks. We have a radar imager, and we have also very sensitive Sherlock, like Sherlock Holmes. That's an instrument that can detect, that is a detective to detect organics, making use of Raman and luminescence. So some very nice space photonics technology that we could use for future missions. And then there is the SuperCam. SuperCam is both a camera, but also include a laser beam that is shot at the rocks and then can, through laser-induced breakdown spectroscopy, can measure the composition of these rocks. So you have seen some of the first images of Perseverance. So that's an overall context where so my research group has been involved as co-investigator in some of the instruments on board Mars Express and on ExoMars, and we collaborate as well with the Mars mission interpretation, also by a joint analysis in the field that we describe later. Now, let's go back to Earth, because I've been also involved in mission going to the moon. And I was leading the first mission to the moon of Europe, which was launched in 2003, first mission of this millennium. And it was European, but in the meantime, we didn't do another one. So hopefully, so we'll have ExoMars. We'll have some ExoMars to Mars, but we have also some mission to the moon planned at the end of this decade. But I wanted to share these images. It was a mission where we were testing also solar electric propulsion. So we launched from Earth, and we use only solar electric propulsion to recede from Earth. It took us 1.5 years, but on the way we could monitor our own planet, make some image of Europe. I think I see Latvia. You can see the top left. It's a very atypical image of Europe, where the Holland, where I am now, and Latvia are completely sunny, and the southern part of Europe are cloudy. So that was the first image we took with our camera, and then as a function of time, as we were further and further from the Earth, we could take pictures, and then the whole Earth came into our field of view 1 year later. And then we were put in orbit around the moon using solar electric propulsion. We also got closer, and here actually is an image of the Earth from the surface of the moon. So we use a set of instruments. In particular, we had the cameras here, and we used it observing some of the Apollo, like Apollo 15 landing sites here. That's where you can see a rim, which is a lava river, and that's a place also where there was a rover from Apollo 15. You can see its location. You can see also on the top right where it is on the moon, using a drawing that even Galileo did 400 years ago. You can see its location. And so we could then compare remote sensing observation from orbit and surface, also as a way to prepare for the next future traverses of robotic and human mission. We also looked for Apollo 11 with our camera. And to be frank, this is a place where Apollo 11 was supposed to be, we didn't find it. And the journalist said, oh, yes, Apollo 11, that's a hoax. But indeed, at this altitude, we had a resolution of only of 30 meters, so we could not see the lander. But later, Lunar Reconnaissance Orbiter, which has a resolution of half a meter, could see very well the lander and even some of the track from the astronauts. One important contribution from a smart one, because we had a elliptic orbit close to the lunar south pole, 300 kilometers from the lunar south pole. We had a very high resolution mapping of the south polar region, so we could create a mosaic of images of the south polar region, where you can see some area in permanent shadow. You can see also illuminated area, and this would help to prepare the next exploration. We could monitor the moon over all year and see also some seasonal effect at the pole. And even we detected close to the South Pole a place which is almost always in sunlight. We call it the Smart One peak of light, and that's a place where everybody now is trying to go with a scientific mission or to put a human base. And so we have to see how we can help and also how we can harmoniously occupy this Smart One peak of light. Eventually, we ran out of fuel, and then because the orbit around the moon are quite unstable, then we were destined to crash on the surface of the moon, but we made some little correction to touch down at a specific place and a specific moment, and then we could even observe the impact. And then after we searched for the crater created by Smart One, which was on a very grazing incident, and it took 10 years to find the crater, a very elongated structure, and you can see also some of the ejecta, which were a bit like a butterfly wings for such grazing impact. And here in the laboratory, we reproduced a bit the geometry of what you expect with such a grazing incident. So Smart One was alone around the moon for 3 years. But then in 2007, we had 2 missions that were launched in September, one by China, Chang'e 1, and one by Japan, Selene Kaguya. And actually, we use a Smart One previously, sharing our data, but also we collaborated with the successive mission with our experience and also in the science team. In the time, for instance, we provided some ground support for the Chang'e mission, providing some critical information during injection around the moon, critical phases, but also we had a ground station to receive the scientific data, so we could double the amount of scientific data from Chang'e 1. And we collaborated also with Kaguya, which were very ambitious mission. You know, it's a 2-ton spacecraft compared to the 400-kilo Smart One, with several sub-spacecraft. And for instance, they could map the gravity field of the moon, while the Chang'e 1, in addition, mapped with a microwave the subsurface temperature of the moon. Also, at that time, we were contacted by the Indian Space Research Organization to collaborate on their first mission to the moon, Chandrayaan-1, and I was put in charge to negotiate the agreement with India, and we placed 3 instruments from ISA on board. So 2 inherited from Smart One and 1 precursor for our mission to Mercury, Baby Colombo, but also there were 2 US instruments. In particular, there was very interesting discovery of hydration in the poles of the moon done by Chandrayaan-1. In 2009, there was also a launch of a US mission, the Lunar Reconnaissance Orbiter, together with L-Cross impactor, and there was a campaign to observe the impact of L-Cross, a bit like we did for the impact for Smart One. And this found some presence of water ice in the pole to an amount of 5% in the top 1 meter of the surface. So here are some big discoveries from those missions. This is from Kaguya. beautiful views of the gravity field on the near side, on the left, and on the far side. And you see very different compensation of some of the basin and mass that are present there. So big difference actually between the near side and the far side, we don't really understand. This sense also in topography, where the far side see a very big bulge around its equator with high altitude, but also a very giant impact basin called South Pole Basin, biggest in the solar system. So from that, you can also derive the thickness of the crust, and you see also some tectonic structure. For instance, on the you see the far side, but also on the near side, you see Procellarum, a very big tectonic structure. And there was also very interesting high resolution terrain camera that had a resolution to the 1 meter level, and that could monitor a number of geological targets, and also could discover, for instance, some skylights into lava tube. One also instrument was a radar, subsurface radar from orbit, that could measure subsurface layers, and then from that you can see some different volcanic episodes, volcanic layers which were placed in at different times. We were even able to detect some counterpart of some lava tubes, which seems to be very immense structure. Lava tubes on the moon, because of the lower gravity, can be much bigger than on Earth. So you could build cities of 10 kilometers under the surface of the moon. And also there was some very interesting study of the age of some of the volcanic maria, in particular an area on the near side where you have some of the most the youngest part of the moon on the surface, which have an age of 1.5 billion years, and which also correspond to places where you have some anomalous heating and some anomalous radioactivity. So as you see, with all these missions, we have really unveiled a new face of the moon. And there are still a lot of work we can do on analyzing some of this data. And that goes along a roadmap that we proposed with the International Lunar Exploration Working Group, a group between the space agencies, space academia, space industry, promoting lunar exploration. First phase, exploring from orbit, we have done it. Second phase would be to emplace a robotic village with a permanent robotic presence. And then we'll have a phase where you have some short duration human mission on an outpost, and then something where we'll have some permanent presence of human and robot on the surface. So we call that the Moon Village roadmap. And for this, what do you need? You need to go to the next stage of instruments. So this were, for instance, the instrument we had on board Smart One. So very miniaturized photonic instrument, measuring some of them. We are measuring in X-ray. So 5 kilos toaster, which is about 5 times lighter than some of the other X-ray instruments flown by other agencies. We had the infrared spectrometer, also 2.3 kilogram. We had a camera of 2 kilogram with a sensor which was the size of a human eye. And we had also some plasma diagnostic instrument on 2 booms and some deep space communication in the Ka band. So as you see, our baby, Smart One, was the most wonderful baby with vision in X-ray, infrared, and a nose, 2 nose, and even very sensitive ears for radio data. So now we have tried to develop an academy with a program called EarthMoonMars that was supported from ESA in the beginning, so some 15 years ago, also by NASA, by some universities in US and Europe. And we have developed a system of modules of training for young professionals. They don't need to be from a space university. We can bring space to them. And so we started with some courses of space science, space technology, space science, astrophysics course, planetary course, some instrument, space technology, system engineering, even space architecture, and also some technical course. We had also started some 15 years ago a program of hands-on training in the field to test instrument and also to test astronaut practice. And so this we call astronautics hands-on training. So we do analog survival mission where we see the operation of a crew in an isolated base, in an habitat. And also there are some physical activities like a zero-G test, IG test, or diving, and also basic human performance training. But as well, we collaborate with some group that develops small rockets, like so a group in Poland, but also here a group in the Netherlands or in Switzerland that develops some rocket, and even some stratospheric balloon mission. We also have incorporated some 10 years ago, another dimension to this training is to incorporate the human aspect. Of course, for astronautics, you need to address the medical aspect of humans, but also the psychology, the interaction between a crew of different cultural origin. And so we have also incorporated this element in the training, humanities, diplomacy, and even we invite some artists, architects, designers to be part of this. And more recently also, we wanted to develop a program of sociopolitics, space diplomacy, space for peace, inclusion with space, diversity with space. And because I know there is really a threat on this diversity, and diversity is something very important in the build-up of the space renaissance. So we call it Space for All. So 4 years ago, we got also a grant from the European Union to train space entrepreneurs. And so we incorporated a fourth pillar on management training, business, and economics, project management, mission management, looking for sponsors, how to manage your careers, and also how to create a space startup, making use of the very good program that was put by ESA with the BIC, the Business Innovation Center and Space Business Incubation. And we develop also some activities how you can make business using data from space. And also another important aspect is how to share some of this space education with the public. And so we develop also tools for young professionals to learn to communicate, to write, to go on TV, to go on radio, or to write also social media stories. So in practice, so we have also developed some program to build instruments. So 15 years ago, there was a competition, Google Lunar Prize, that would give $20 million to the first commercial lunar lander. So we collaborated with some of the team, and I built a prototype mock-up lunar lander, mostly from the point of view of testing how instrument could be put on board. So we had some rovers, we had some spectrometers, some cameras. I didn't deal with propulsion rocket side because we could not have a propulsion test at ESTEC. I focused on what happened to the lander after it's landed in terms of science and exploration. And so we worked in particular with a team from Japan that developed a small rover. You can see me with in our EarthMoonMars yard at ESTEC testing the rover. This was called Akuto. And that's the same team that the year right after created a company called iSpace. And this company iSpace now has more than 300 employees, and they have built a lander 3 years ago that touched on the moon, and they launched again 15th of January their lander Resilience. So we have done the test with this lander in the field, in environment, in STEC first, but then in the field, in environment that look like the Moon and Mars. And so more recently, we have tried also to develop systematic payload activities, and particularly in the area of space photonics, where, okay, on one hand, we deal with cameras. So we have been working with very sophisticated cameras, like the one which are on board of HRSC, or that we fly with the ExoMars rover. But we have also some lab cameras that we are integrating, or we put them on the lander, or put them on rover. We do some work also with some telescopes. We put some telescope on the lander, and we collaborate with some teams also that put the telescope on the moon. And we do some terrestrial tests of telescope, portable telescope, that we operate, and also some radio instruments. Of course, we are also, as astronomers, sometimes we have access to the big telescopes, and we are looking forward to the opportunity to come to Baldon again and make use of your telescope, possibly with some instrument that we could bring on. And in particular, here you can see on the top right, it's a test bench where we have an imaging spectrometer. That's an orange instrument there. And we use it, for instance, to do some spectral images of a sample, like meteorites or analog sample from some of our fieldwork in Moon-Mars analog. We have also a Raman spectrometer, and we do have also reflectance spectrometer. And so we are looking, we use them to analyze samples, but also my collaborators. So we have a Dr. Mojtaba Rauf and Dr. Also Peyman Soltani. They are developing this hyperspectral imager. They have not only analyzed samples, but also they have adapted this spectrometer to a telescope. So we have some small telescope, and we look at the possibility to come and to install it on the Baldon Observatory during maybe possibly a workshop in June that we planned. We plan a space student workshop in Riga in June, and also sometime at Baldon. So we do some work on sample analysis. We do some work on rovers. We have also one special interest on organics. This is from another area of my work, where I've been studying the largest organic molecule in space from their signature of interstellar spectroscopy, where I discovered the fullerene and polycyclic aromatic in space. We put some organic in space on space station, and now we are interested how they could be detected in ice environments on our moon or in some of the icy moons of Jupiter and Saturn. And I got a special grant for that, where so I will have some students working on this. So we have also developed some activities for testing miniaturized instruments, but together with so I've hired a special project manager for payload and for CubeSat. That's Dr. Mojtaba Rauf, that will come with me in a future visit in Riga. And we have also developed now a project of an education CubeSat, so Earth Moon Education CubeSat, EMEC. So, and we have started that with some 8 students from different universities and technical schools around Leiden. And the next 6 months, we will have some bench studies, some prototype, and we look to develop one CubeSat for Earth observation that will incorporate some spectrometry, and to have also one CubeSat that could be brought to the moon, eventually on the surface rover. And so there is also some synergy with some testing how to put yes, a camera and a spectrometer in the back of a telescope that we could test jointly in the frame of the ERA chair for space photonics. So in previous campaign, we have used also other techniques like X-ray diffractometry, X-ray fluorescence. In particular, we had a collaboration with the NASA Ames Research Center that put such instrument on the Mars Curiosity rover. And actually, this orange suitcase is a terrestrial field version of this X-ray diffractometer. Dave Blake is an PI, and we worked with him at NASA Ames. We had also visible infrared reflectance spectroscopy, Raman spectroscopy. We also look at microscopy or close-up imaging camera. And in particular, you can see in the lower right, some image of samples we had in the desert of Utah, where you see some rocks, but they are covered with a film of cyanobacteria, algae, and lichens. And this is with microscopy and with also analysis of the composition. That's something that could be preparatory to the search for life on Mars, for example. In the desert, we even had the possibility to analyze some samples. So we took some samples from a number of sites and we analyzed them in very sophisticated laboratory for carbon content, amino acid, polycyclic aromatics, and even we could perform some DNA analysis. So that's some of the experiments we used in the lab before. But these were used in particular into collaboration with NASA Ames and some labs that we had in Amsterdam and in other centers. But we wanted to bring this lab close to my office. And for this, we built an ExoLab. ExoLab is a small lunar lab that we installed at ESTEC and where I would lock my students for a few days. And so that this way they can train the protocol of working on the moon or Mars. So here you see 4 of my students from the Super-Aero Engineering School. They have some joystick where they can pilot some telescope or some rovers or instrument outside. But they have also some sample analysis experiment, microscope, spectrometers. They have also a 3D printer if they need to bring some accessories. And they have a dark area for dark spectroscopy also for resting. And so in 2015, also, we started an activity supported by the ESA Director General, Moon Village, where we try to involve a large community to define what could we do on the Moon Village, how to make it happen from the science, what science we could do, what instrument, what habitat, what also social measures. And then we organized a number of events like this. And this led to also some field work where we built a moon base under a glacier in Switzerland. It was a project called ESALab Igluna. So ESALab was a platform to involve multiple universities to work together. And there, for Igluna, it was the first ESALab project, the build-up of this moon base. We had 20 universities that sent some students working on different aspects of this moon base. Some of them were the architecture of the base, some others were experiments, robotics. I brought my lander on the surface of the ice, and we tested it for icy environment. We had also some people growing plants, salad, and using robotic arm and artificial intelligence to pick up the salad. And this was also a way to train young professionals to work in a European team and to learn to go through the methodology of developing a space project. So we have been also involved in some experiment in space about survival of organics in space and of life. And so we flew some experiment on board the International Space Station, on ERDF or before, and then we had RA and Eureka in the early time. And then we had a precursor of Columbus, which was flown on a Photon, a capsule, a spherical capsule that is sent to space for 3 weeks. We launched it several times, and one time we recovered this biopan capsule, where you have a number of samples of organics, of also living organisms, and you open this pan in space for 3 weeks, expose it to the sun and to the radiation, then you close it, and then you bring back the samples. And on re-entry, the photon capsule is burned on one side, but the other side is well protected. And we found some organics that survive well in space, like a big pH or fluorines. And then we flew another set of experiments on the International Space Station on expose E, expose R for exposure of 1 year or 1 year and a half. And on the top right, you can see also a small experiment which was developed by NASA Ames and by Professor Foing, actually, as a project scientist. Was called Oreos, where they had some samples they were exposing to the sun and they were measuring with a small spectrometer the evolution of the sample. Actually, I have in my lab the same spectrometer that was used on this CubeSat. So we have also some project developing some tests in the field. You can see here it's almost the moon, and that's a campaign we organized in Etna in July 2021 in the middle of COVID. And I had 12 students from different universities in Europe, but they didn't have authorization to come to Holland. So we found a possibility to meet first, and we met in Etna. There was a window where we could meet. So we developed a whole experiment where we launched a shoebox, and then we deployed some cameras, we deployed some rovers, we launched a rover to pick some samples with a robotic arm. Then you bring back the samples for analysis with a spectrometer, and then we try to venture to very dangerous terrain. And so this was a way to get them familiar to the old protocol of what you could do with a robotic system on the moon or Mars. So this was in the middle of the COVID. The year after, we could join even a much more extensive campaign called ROBEX Arch, which was organized by the German Aerospace Center, DLR, where they deploy 2 intelligent rovers, and they had a system with a robotic arm where they could take from a lander some shoebox instruments and deploy them on the surface. And they could deploy some 15 of this shoebox. 4 of them were used, for instance, for radio observation, interferometer, but others were used for seismometer, for sample analysis. One had a LIPS from the Planetary Institute in Berlin. And so this is, in fact, the way we could deploy experiment on the surface of the moon with an intelligent rover. So in parallel, ESA also brought a bigger rover, which was teleoperated by an astronaut. And the astronaut was Thomas Reiter, which had flown 500 days on space station. But the astronaut was operating them like he would be in orbit in the gateway, so in orbit around the moon, and he could really monitor and drive some rovers on the surface and do some science. Actually, we have done some tests before, already, some 15 years ago, of the collaboration between astronauts and equipment on the lunar surface. So we had our Google Lunar Express lander, ExoGeoLab is the name, and then we sent an astronaut to repair, to inspect, to maintain, and to operate some of the instruments. And we did that in a moon analog in the Eiffel volcano region. We even sent our lander to Mars because actually there was a campaign simulating travel to the moon and Mars. And this was in Poland, in a base, in an ancient military hangar, where now they have built a Moon-Mars base. And so we participated to a campaign where we brought our lander, we put a telescope nearby, and we could teleoperate the instrument from the lander and the telescope from remote. So from Holland, we could teleoperate this lander and telescope in Poland. So this was a kind of our side of learning with a young professional how to operate mission, but in parallel, China managed to land in 2013 a beautiful lander. The mission was Chang'e 3 on the near side of the moon. And this deployed a rover called U2. And there was even a telescope, ultraviolet telescope, that has been observing the Earth and also the Milky Way, the sky. And this has been in operation since 2013, so 12 years of operation. So we have had permanent robotic presence since 2013. So the robotic village is alive. So, so the robotic village continues. So we had missions from commercial, some Indian mission, and we had also some commercial mission, like from the CLIPS program. You know, last year in January, we had Intuitive Machine 1, IM1, which landed in a Malapert mountain. So they flipped. So it was not fully successful, but I mean, they managed to land softly. And I am now part of a team, a company called Cosmosis, where we provide scientific support as a chief scientist. And this team is building a lander for 2028 to go to the surface of the moon. So after this robotic presence, so our goal is to have a sustainable presence on the moon. And you can see in the recent years, we had many missions to the moon. You know, there was one mission, Smart 1, 2003, 2006, then a few orbiters, but since 2013, we had the Chang'e 3 lander, and then 2018, we had multiple missions from various governments and various commercial actors. And this, we have also a goal in Europe to have a lander, but this will be for the end of the decade. I have been always dreamed to be part of the open lunar lander. So I worked on this project already some 25 years ago, but it took us a lot of time to develop a lander. We had one in collaboration with Russia, but we stopped. But now there are many commercial actors and many countries that are developing a lander. And then in parallel, we have this program of a human to the moon, with the Artemis program from the US and the International Lunar Research Station program led by China. So Artemis 1, as you know, Artemis program. So you have a capsule called Orion capsule, which is for 4 astronauts. And this is brought by a European Service module to the moon. And this European Service module is a critical contribution to the whole Artemis program, providing, you know, the consumable air, water, the right temperature, the right power, and the right navigation to go to the moon and then re-inject the capsule for the proper angle and location for a safe re-entry. So that's how it looked like. I went to the first launch of Artemis 1 with this capsule. And as you know, the Artemis program is looking to have so a launch every year. So there are some delay at the moment, but there will be also various phases where you will have some surface expedition, a lunar terrain vehicle, a crew landing service, a pressurized rover. One will be contributed by Japan, and there will be also some surface habitat. So how can we help to prepare this moon village implementation? So there are various tasks, how to get there. So that's for the rocket people, for SpaceX, for Blues, for Ariane Espace, and so on, for China rocket. So, but we can contribute to optimize how we are going to operate, communicate, work with human and robot, ensure survival, ensure mobility, use resources that are locally there, power, but also minerals and others. And we try to do that in collaboration with the users, which are not only the old space actors, but also new space actors, but also industries and entrepreneurs from terrestrial companies, which know how to operate system on the surface of a planet like the Earth. And so we started already some 15 years ago to develop some programs where we go to analog site of the Moon and Mars, and we went to Etna, as I've shown you before. We went to the Utah, which is a very good analog for Mars, Utah Mars Desert Station. We went to a few campaigns to Iceland and Chile, but more recently also we have access to a beautiful base, which is on the Hawaii Mauna Loa volcano, halfway to the summit, where we have a base which can host 6 to 10 astronauts. It's with solar power, and it's autonomous. And when you are going out, you are really surrounded by a landscape that looks like the moon and Mars. So we started actually in a campaign, and that's how we created the EarthMoonMars program campaign in 2009, where every year we would go to this Mars Desert Station to do some studies, comparative geology of Earth and Mars, and testing some experiments for astrobiology, geology, and life science. We brought some cameras, spectros, rovers, drone, radar, and drills. But it was also the opportunity to be aware of what type of habitat you need to survive and work on the moon or Mars. So we look at habitat aspect, architecture, the power systems, the recycling of water, how to run the laboratory. And of course, it was a way to solve a lot of human issues. So how to be performant, how to also perform extravehicular activities, what is the food, medical studies, and also intercultural and interactions, psychology of a crew in isolated and extreme environment. And it's also a great platform for training young and advanced researchers, sometimes together, and also for outreach. So every year since 2009, we had some campaign where we would have 2 or 3 a crew of 5, 6 people that we would send to the Utah desert for some expedition. And one of the rationale at the beginning was really Mars related. You know, we had some of first images for Mars Express HRSC, and we were looking for places on Earth that look like what we were seeing on Mars, and we found it. Some ancient rivers or lake, which have some features very similar to what we found on Mars. So we had also some instrument that we tested outside. We had a penetrating radar, we had some drill, and we would take drill samples of 2 meters and analyze as a function of depth what was the variation of composition and also of biology in this sample. Sometimes when we were too lazy to go outside, we would just send a rover to do some of the precursor tasks. Now we have access to this base in ICES. So that's in Hawaii, in Mauna Loa. That was built in around 2015. It was used for 3 years for long duration psychology study together with NASA to see how a crew to Mars would survive for 1 year. But now we use it also for short duration mission, like 1 week or 2 weeks, simulating what you would do on the surface of the moon. And so the founder of this is Hank Rogers. He's the owner of the Tetris game. So he has invested a bit of his wealth in developing this facility, but also we work with NASA, University of Hawaii, and EarthMoonMars to use it for research. So in 2022, after the COVID wave, we had another wave, which was a lava flow giant eruption that flew on each side of our base, but luckily the base is high enough that it was not destroyed by the lava. And so, so 2 years ago, we went there and we did a full simulation with Hank Rogers, our commander. I was the chief scientist. We had some geologists, some architects, and some psychologists in the crew. And we use also the base for research projects. These are some of my master students from geology in Amsterdam that did their master research, taking some samples from the surface or from lava tubes there and writing their thesis or some article on the result. Here you see the document well the context for each of the sample, like a professional astronaut on the moon will have to do. So what happens in the last year? A piece of news. So we had, I joined this company Cosmosis as chief scientist. So in exchange, they provide some donation to EarthMoonMars. And then for this, I can pay some project managers or some students. We are also developing with the community some payload meetings to see what payload we can help the community to develop for future opportunities. We organize also some conferences at COSPA, at ISC, and so on. And we have a various collaboration in Europe. So we had this project, Eurospace Hub, which was funded by EU for 2 years. Now we are preparing, we have prepared another proposal called Green Space Hub. And we have also some proposal that we have established with Riga, Latvia universities, Photonika, such as this ERA chair for space photonics. So we organize campaign for astronauts, also campaign for fieldwork testing our instrument. And we had also some activities to scale up some small companies in the frame of our Eurospace Hub platform. Now, we have also started with Leiden and Delft universities and schools from education CubeSat for Earth and Moon. So the project manager is Dr. Mojtaba Raouf, and we have some 8 students at the moment. And so they are starting now, and we hope to bring some of them for a student workshop that we will have in Riga at the beginning of June. And we have also developed some projects for space humanities, like Space for All or Space Renaissance for All Gallery. Here are some examples of, so the students that are with us have also the option, in addition to their individual project, to experience the life of an astronaut. So they can participate to this MPOL, EarthMoonMars Polar mission, where they are 1 week in a base together with other researchers without window. And here you see some medical students and engineers working together for that. So some example of results for some of the students. And so these are slides prepared by them. And so Thais Zuketis, she did an architecture master last year, and her topic was about the design of a lunar habitat, about the well-being of crew. And actually, she did a 1 week campaign isolated with 5 other analog astronauts. And she learned really what it is to be an astronaut, and she could inject that in her design and got cum laude for her thesis. So another students did also a 1 week stay in the habitat, but this time with only 2 people. So that's Clara Laforêt, a French student in a human robotic partnership, and Matthew is an engineer that likes robots. And they simulated what would be a 1 week mission on the moon, like Artemis 3 will be, with the first women on the moon. So they did some psychology studies, radiation, virtual reality. They had a rover as a companion, but also in the middle of their campaign, there was a huge solar storm. So we simulated 3 days of blackout where they survived very well. So this is how the Artemis, the habitat looks in this for this MPOL campaign. This is an analog astronaut training facility in Poland, near Krakow. So they have a lot of space there, and that, but it's mostly focused on doing research. So they have a quite a heavy workload, and also they have to practice gym 1 or 2 hours per day, like the astronaut will have to. And so this, we want to open it to all students interested. So we have a special program where we can co-fund the cost of 1 week there. It's about 650 euros per week. We can pay half of it. In exchange, the student have to do some research, write some abstract, and write a draft of an article. But it's a nice project to have the experience of being an astronaut. Another student, Elena, she's a Polish student, but from Eindhoven University, and she also did a campaign simulation. In her case, she had a crew only with women. So we could answer the question, is it better to send only women to the moon? And she was together in particular with another collaborator, Jasmine. She's a psychologist, PhD. Actually, her PhD is on exopsychology. So what is the psychology in space? And she developed some measure to create well-being using art, sound, and even calligraphy. So all the students from our academy have the opportunity optionally to be part of some of this campaign, and we would like to invite also some students from Riga that could join some of this international crew. Now, this is in Poland, but also we have developed a facility, a small habitat that is mobile and can go from place to place. And here we installed it at the Space Business Innovation Center of ESTEC. And here you can see some members of our team. We have also Fateme Fazel here, and she's attending here. She's my special project manager for machine learning and AI for space data. But we have various team members that contributed to use a mobile laboratory that we installed. So this is called Exospace Lab Express. So it's a laboratory with the science racks, some instruments, some spectrometer to analyze samples, and also for some physiology studies. And you have the possibility to inflate a structure to make it bigger. And so the inside you have also a compartment with 2 beds for privacy and for rest for the astronaut. So we use it for research, for training young professionals, but also for outreach with schools. So we get schools visiting it. So we were part of an event Science Week, for instance, where we had more than 2,000 visitors looking at our habitat. We also organize astronomy sessions, stargazing. So this was done in the south of France, where we had a good condition. In Holland, we don't have always so good conditions, but still we try to have a program where we try to observe the sun at least once per day, and we also observe the moon and possibly some stellar targets. We even developed some project where we use our spectrometer. You can see a spectrum here to analyze rocks, but also we can analyze plants. And from the plant, we can analyze the health of plants. And we developed a program with some amateur gardeners, so a citizen lunar garden program, where we grew for them some plant and we monitor the health over weeks. And this is using a spectrometer, the ocean optic spectrometer that is the same that the one we flew on the CubeSat Oreos business IAMS. So we have also a program where we organize field work or workshop, and this is in Volcano Island, in one of the Aeolian islands. So there was an astrobiology school, and I had some 10 of my students participating to the field school, and using instrument to analyze or to prospect or to explore and to analyze samples. And then we went to Etna, which is a much bigger volcanic island, but also we were at the astronomical observatory of Catania Observatory, the Serra La Nave, where we could do some astronomy. In parallel, we have also developed some human or humanistic and social project. One of them is EarthMoonMars gallery, where we want to send a gallery of art to the moon. And so we code and we have 100 pieces on a gallery 10 by 10. But as the price of a transfer is about €1 million per kilo, we miniaturize a gallery where each art piece is only 1 centimeter. And then we have a prototype that is ready to launch the moon. We have also developed version that we launched to the International Space Station with 64 art pieces. And this was in space for 1 year and a half. And now we have also just finished another small gallery, which is called Space Renaissance for All, exploration gallery. So that's, we just integrated at the end of November. And this included some biology samples, astrobiology samples, some mineral samples, but also some art samples, 20 art samples, 20 science samples, and also some logos of some partner organization for our Space Renaissance initiative for space SDG 18. And so we delivered it to the company in December, and it's now is scheduled to be launched on the capsule. It's called Mission Possible, together with the Exploration Company and launched by SpaceX in June. And so that's how it looks like. So you have actually some of the trays, which were the same trays that we flew on board of the International Space Station. So we created 2 of them. And then some tray contain some little glass disc with logos of some of the partner organizations. We have the UN, we have IF, we have COSPA, we have some universities, we have some seeds. And also on the lower part, we have some biology samples, we have some meteorites from Moon, Mars, asteroid, and we have also 10 art pieces. So as you see, that's very diverse. So we have been working in particular, thanks to the funding from the European Union, EIT, for our Eurospace. We have been working with Venus, with international space universities, with Madrid Complutense, but we have also, you can see an agreement with Riga Photonics, with University of Latvia in our project. So now this is the number of projects that we have conducted so far, but in the past 3-4 years, we have had some intense collaboration with Photonika, with the Latvia universities, where I'm guest professor, but we have also made a proposal for ERA space share program on space photonics. And there we are building on various aspects. So we want to continue some collaboration on space data analysis. We want also to connect with some of the research projects that could be done at Baldon Observatory, and also with the laser team that is in Riga. But something specific, we want to develop a space photonics laboratory with various instrumental techniques to analyze samples, or to, in particular, in the area of imaging spectroscopy. Now, we think that there is also a good opportunity for CubeSat and miniaturized instruments as a way to perform research, but also as a way to develop an innovative solution. And so that's something also that could be, we could think of a CubeSat developed at Photonika. So we have also prepared a program of space training of a student, and building on the experience of what we have done with the EarthMoonMars in the last 15 years. And so we are planning to organize some space workshop for students first week of June, and also some opportunities for local students together with international students. Also, the experience that we had with the space innovation business, with ESA, with EU, with Eurospace Hub, could be also extended to activities with a space chair at Photonika. And this can build up also some momentum to create participation to ESA and to some of the mission through payload, also from the science side. And another aspect, Photonika is has developed some great collaboration with other universities in so-called teaming project. And I think we can also contribute with some of the research that I've performed with EarthMoonMars to this. So that's more or less the program. Now this year, we have also a function with EarthMoonMars to organize or to participate to some international events. Like I was in China for a space planetary event. We will have some event at Vienna for the United Nations Copious Science Technical Committee, where with Space Renaissance we are a member. We have some good opportunities to meet at the Paris IF Spring Committee meetings, where we are defining the program for the next International Circle Congress. We have also some sessions and for the European Geoscience Union. And actually, I'm organizing a session on the planetary instrument technologies. And we just have a session where we receive like 56 abstracts. And we have also lunar session and Mars session. So it could be a good opportunity to present some of our results, but also to meet some of the community. Beginning of June, we plan to organize in Riga a space students workshop that would be including some time in Riga, but also possibly a few nights at Baldon to show to the student how to use a telescope. And then there are also a few other events. In particular, in the US, we have a launch of our Space Renaissance for All Gallery in June. We plan to organize some events there. There is also very interesting school over the summer, the so-called ISU Space Studies program from July to August. And there are opportunities for young professionals to really join a community of 150 students from all over the world. So I would recommend if you could identify a few students that could take part in this ISU SSP. And then we have a big event in Helsinki, the European Planetary Science Conference, 7 to 12 September. So close enough to Riga. So that's something also where we could have a good presence from Riga. And we have the International Circle Congress at the end of September, beginning of October. The abstracts are due at the end of February, so we are expecting a very large contribution for that. So that's some of the events coming up. We will have also every year now on 20th of July, we are celebrating International Moon Day. So this is for what we did last year. So that's something also where we could organize a nice event in Riga and with other partners. And here, actually, I had the opportunity to write an abstract for Houston LAPSC, and I wanted to put the list of all the recent collaborators of the last 4 years. And I want really to pay credit to all these collaborators to the different group. And you will see, you will recognize also some colleagues from Photonika, Arnold, Aigars, also Vid Beldav is a strong collaborator, and some others. And some of the students that are starting with our CubeSat project and some of their supervisors. So you see, we are trying to maintain a community of research, also developing a training for young professionals. And we hope that they can be integrated for some of our research efforts, in particular with the ERA space space chair program at Photonika. So I want to thank you very much for your attention. And if you have some questions, I will be pleased to answer.